Hello, and so this is video 2 of section 4.3. So we wrapped up last time, we defined what a basis was, and we looked at a couple of bases. Now I want to go over bases in Rn, because given the tools and the knowledge we've built up thus far, we actually have a way of determining, if I'm presented with a set of vectors, whether or not that set of vectors is a basis for Rn. So, if I'm given v1 through vp vectors, and I'm asked the question, is this a basis for Rn? Four-step process to determine if this is the case. First, because this is linear algebra, we're going to set up a matrix and row reduce to reduced row echelon form. So you let A be the matrix whose columns are just given by these vectors, and you reduce it all the way down. Note that this process closely mirrors the process of checking whether or not a set of vectors is linearly independent, right? Because that is one of the qualifications we need for a basis. So remember, we need to check for two things now after row reducing, one of which I've already said is linearly independent. The second, we need to check that this set of vectors spans Rn. Well, we can call on a theorem here from section 1.4 that says if this reduced row echelon form matrix B has a pivot position or a leading one in each row, then the span of this set of vectors is equal to Rn. Depending on how you like to look at matrices, this is sort of also, if you remember the linear transformation sort of analogs, this is the same quality we check for when checking if our set of vector, our matrix is onto, right, is number 2, and 3 is actually the same quality we might check for if we're checking for 1-to-1. Not important, just sort of interesting parallels that are going on. But so if I reduce it and I get a pivot position in each row, then I know the span of this set of vectors is equal to Rn, so that would be check 1. If B has a pivot position in each column, then this set is linearly independent. So if I can look down each row and see a leading one, and look down each column and see a leading one, 2 and 3 are satisfied, and this set of vectors is a basis if and only if 2 and 3 hold. So we have this nice way of checking for if a set of vectors in Rn is a basis. So let's do an example or two. So there are 4 examples on your worksheet or in the notes. So there are 4 examples here. I'm going to do numbers 1 and 4. I would encourage you to do 2 and 3 on your own, but when I post the solutions, I will post the solutions to those as well. So we want to determine if the following sets are bases for Rn. So the first set we're given is the set 1, 0, -2, 3, 2, -4, and 3, -5, 1. And so again, the first thing we're going to do is set this up as a matrix. Feels like it's been a while since we've row reduced a matrix. And we're just going to row reduce this to row reduced echelon form. I was almost beginning to miss row reducing. So here I'm just sort of following the generic algorithm. I'll try and speed this up a little bit. So now notice I can do a couple steps at once because I have a pivot 1 here. I can clear out that -3, or the 5 and the -3. So I can do 5 row 3 plus row 2, and -3 row 3 plus row 1. And we're kind of getting in the clear here now of the row reducing algorithm, because I always think like once I get that 1 there, the rest is going to be fairly straightforward. So we do 1/2 row 2, and then one more step. All right, so start with our set of vectors, create a matrix, row reduce. We've got our row reduced echelon form, and so now we want to check, does it have a pivot in every row? Yes. Pivot in every column? Yes. So therefore, this set of vectors, 1, 0, -2, 3, 2, -4, and 3, -5, 1, is a basis for R3. So normally this is how you would, so if you were given a set of vectors and you maybe didn't have another way, and we'll see with a couple more examples, sometimes there are ways you can get around having to do the full process. But given a set of vectors, this always gives you a foolproof way to determine whether or not you have a basis. So I want to quickly look at 4. So 1 and 2, in this set of 4 examples I gave you on your worksheet, 1 and 2, you have to set up the matrix and row reduce, but 3 and 4 you can actually get around needing to do that by sort of calling on some old facts that we have talked about previously. So 4 gives you the following set of vectors. And so 4 asks, okay, we've got this set of vectors. We want to determine if it's a basis. So what are the qualities of needing to be a basis? Well, remember, it has to span R3, right? And for all we know, these vectors could span R3. But the second quality that these vectors must possess is that they must be linearly independent. And if you remember, we actually have a fact that if there are more vectors than entries in each vector, then the set is always linearly dependent. And so for 4, you can actually just immediately verify for 4 that this is not a basis. Because these vectors, no matter what, I don't even have to do anything to check. We just immediately know that these vectors are not linearly independent. And I apologize for being a little distracted. There was a spider crawling on my wall, so I was a little distracted by that. But anyways, so we've seen 1, right? 1 gives us a basis, as we showed. We've seen in 4 that we don't have a basis. If you work through the other 2 problems, 2 and 3, you will actually be able to determine that 3 also is not a basis. And so notice that the reason 3 is not going to be a basis is sort of the opposite reason that 4 is not going to be a basis. So 3, you're given 2 vectors, right? And if you imagine what's going to happen with the row reduction there, you're never going to get, right, if you only have 2 vectors, you will never actually get a pivot position in every, you will never get a pivot position in every row. And so, looking at these examples, we can already see an interesting fact that every basis for Rn, and there could be a ton of them, well, there are infinitely many actually, must contain exactly n vectors. So this is a huge fact right here that you actually know, because if you contain too few vectors, well, you'll never be able to span the whole space because you'll never have a pivot in every row. If you contain too many vectors, then as we've seen, you won't be linearly independent. And so every basis for Rn, you always have to have exactly n vectors. So if you're given a set of vectors and asked, is this basis for Rn, and the number is not equal to n, you can just immediately say not a basis. All right, so what do we do with something like 4, though? So if we have too many vectors, right, like for all we know, the span of 4 could still be Rn, it just might not be a basis. And so what I want to end with is the spanning set theorem, which tells us how maybe if we're given too many vectors, we can whittle down the number of vectors to still get a basis. So the spanning set theorem says that if we let S be a set of vectors, v1 through vp, and in any vector space V, and we're going to let H be the span of this set of vectors. So remember, H is a subspace of V, and H is just equal to all linear combinations of these vectors. So what our spanning set theorem tells us is that if one of the vectors in S is a linear combination of the others, then we can remove this vector from S, and the remaining set still spans H. So what this means is that basically if this set is linearly dependent and its span is equal to h, well, I can remove that vector that was making it linearly dependent and not change the fact that it spans h, right? So like, it's sort of saying if I have too much information or redundant information, I can remove the redundant information about my set. 2, if h is not the 0 subspace, right, so just the subspace only containing the 0 vector, then some subset of S is a basis for H. So the proof of this I'm going to leave as an exercise in your on the worksheet. So the full proof of this is I'll leave it as an exercise. Try and work through it, and then I'll post the solutions. So I've got the proof for this written out. Basically, I'll sort of give you the rough idea of how it works. So basically, if 1 is true, right, we have some vector in this set that is a linear combination of the others. What you do is you say, okay, write this vector as a linear combination and pull it out. And then anytime we have a vector in H, which needs to be written as a linear combination of these, right, since H is equal to the span of these vectors, we can just sort of rearrange things and never actually use the vector vk when writing these vectors of H as a linear combination, right? So basically, the proof of 1 is just remove vk and show that you can still write every vector in H as a linear combination of the remaining vectors. And so if we can do that, what number 2 is basically saying is, well, since the span of this set of vectors is equal to H and this set of vectors is not linearly independent, just use 1 to continue to remove vectors until this set is linearly independent and can be or does span H. So try to work through that proof on your own. I think it very much, like, working through it will really give you some intuitive ideas, and I think it will really sort of explain what's going on here and why this theorem is so important. But basically what this theorem says is that anytime we're given a set that spans a subspace H or spans a vector space, I can find some basis within that set if that set itself is not a basis. So I want to end with actually the example number 4 that we had looked at, because what we're going to do is we want to find a basis for the subspace spanned by those 4 vectors. And we'll see how to do that. All right, so if we're asked to find a basis for the subspace spanned by this set of vectors, what we want to do is set up the matrix, row reduce, and from the row reduced echelon form, we will be able to sort of determine the subspace that these vectors actually span. And I'll sort of explain why that is once we get to the row reduced echelon form. So once again, we're going to do some row reducing. All right, and so I'll maybe move a little quicker on this one, since the row reducing isn't really the main focus of the video. So I'll do those 2 steps at once. Hopefully I can keep track then. So 3 times 4 is, so that should be a 3. 3 times 4 is 12, minus 5 is 7. 2, 0, negative 1. So -3 is -9, -5, and -2. All right, then I'm going to swap rows 2 and row 3. -8, -4. We do that. We're almost done. Now we just need to clear the row above row 3. So we will do -5 row 3 plus row 2 and -3 row 3 plus row 1. And so what's going to be very important here, so that'll be -3 halves, 0, 1, 0. 2 minus 5 halves is equal to -1/2. And then 0, 0, 1, 1/2. Okay, so notice that this corresponds to, again, we can associate each row with a variable, right? And so if you look at what's happening here, x4 is a free variable, right? Specifically because x4 does not correspond to a pivot column. So x4 does not correspond to a pivot column, so x4 is free. What that means, if you remember that each of these variables corresponds to a scalar multiplied by one of these vectors, that this vector here can be written as a linear combination of the other 3 vectors. So what we can do is say that basically just remove the vector corresponding to a free variable, and say that this set is linearly independent, right? And we know that the subspace spanned by this set is R3 because there are 3 pivots, and so, or 3 pivot rows, right? And so the subspace spanned by this set is R3, and I can find a basis by just removing the free variable, or sort of the vector which corresponds to a free variable. And so in fact, we can do this by just row reducing and then taking each vector which corresponds to a pivot entry in the row reduced echelon form matrix. And so this actually gives us then a basis for the subspace spanned by these vectors.